Now we're going to move on to the concentration unit of mole fraction and percent, and they're very, very straightforward. I anticipate you can do these pretty quickly. So if we take a look at our mole fraction, the goal is to convert everything to moles, and then you've got the part on the top and you've got the whole on the bottom, just like any fraction that you would have. It's just we're dealing with moles, so mass to moles use molar mass. Now notice you don't multiply this by 100 because it's a mole fraction, which means it's the part out of 1. And that tells us that the sum of all of our mole fractions is going to equal 1. Now it's often used to study vapor pressure of solutions, which we won't do till the end, but honestly I've seen it show up at some very unexpected places. Just keep in mind what the name means. We have a fraction, which is the part indicated by the subscript, over the whole, which is the sum of everything present, and it's based on moles. So if you try to think about its name, I think you'll not have to worry about memorizing formulas. The other nice aspect of mole fraction is it can be used for when we have more than 2 components in our mixture or our solution. So that has some advantages in some applications. So let's take a look at our example. Our example I found was a fairly interesting one for this. And it's based on distillation. Distillation is a technique that is often used in organic chemistry. I would be shocked if you don't do it in your sophomore year when you take organic chemistry. And it separates liquids based on differences in boiling points. So they're boiled, the lowest boiling point boils first, and then it's condensed through this tube, and then it's the fractions, they're called, are collected at the bottom. It's also similar to how they separate petroleum components in the oil industries. Now in this case, we're going to assume densities in a mixture. For cyclohexane, I'm not going to worry as much about the structure right now, so I'm just going to call that cyclohexane. And honestly, the molar mass in a problem like this, or the structure, one or the other, would have been given to you. And it's 84.16 grams per mole. And then I have toluene, I'll just call it big T, and its molar mass is equal to 92.14 grams per mole. Now we need to get to moles, and in order to get to moles, we'll have to somehow get to grams, and we have milliliters. We have 100 milliliters of solution. And so what we're going to lay out is moving from milliliters to grams using density, and then mass to moles using molar mass. So we're starting with 100 milliliters of solution. Honestly, you might not have been told that information. You could assume that information because, again, ultimately mole fraction is an intensive property. Pure moles are not, but mole fraction is. So I'm going to go 0.7785 grams. Remember, with a double unit, we always have a conversion factor. Then I want to get rid of grams, go to moles, and that's 0.9250. Now, if you'd assumed a different number, this pure number of moles of cyclohexane would not have been the same. It's when we take the ratio that everything moves into being a consistent intensive property. So I have the same 100 mLs and the density of toluene within that mixture. These are numbers that can be looked up. 8623 grams per 1 milliliter. Again, mass to moles. Hopefully that's refreshing your memory on how we did that quite a bit in pre-AP. And we get 0.9359. Now, to get our mole fractions, our mole fraction of cyclohexane, it's the part, so I'm going to put cyclohexane's moles on top over the whole. You simply add up all the moles that are present, in this case fortunately only 2, and we get a mole fraction of 0.4971, and that's what would be constant. It's a mole fraction, it's unitless. To get toluene, I could set up the same type of ratio, or I could just subtract from 1, because the sum of all mole fractions has to equal 1. And so that would give us 0.5029 for that mole fraction. All right, now let's take a look at the next one, which is percent composition. And in percent composition, we're going to be doing percent composition by mass. It's very important that you specify that you're not doing it by volume, because there's also a percent composition by volume. So you have to be really clear in what you're doing. At our level, we're going to assume it's by mass, but that's not true in industry. You have to be very clear about that. And it's much like what we saw before. We're going to take the part, which is going to be given by a subscript typically. It's going to be the part over the whole. This time it's a percent, so it's times 100, and it's based on mass, but the concept is very similar. And again, this time the sum of all percents has to equal 100, so we can actually get by subtraction rather than setting up the fractions. So let's go back to this. There's two ways that we can calculate percent composition. We can do percent composition within a substance. If we go back to our MTBE that we saw earlier, this is its formula. This is asking for mass within. And I wanted to show you this because it's going to give us a very good conversion factor. So the part that carbon contributes is there's 5 carbons. They each contribute 12.01. And then the whole is the whole molar mass, which we've already calculated earlier, is 88.148. You need to go to at least 2 decimal places on a molar mass. Now, what's implied here is our assumption. What we really did here is we assumed we had 1 mole, so that the whole would be the mass that is equal to 1 mole. And we would get 68.12%. Now, what's helpful about this one is this little ratio right here. We can use this in dimensional analysis, and we'll use it next unit to do what I call a mass to mass within type problem. What it will do is it'll save us going through the mole. So we can go directly like that instead of having to go mass to moles using molar mass, moles to moles using the magic mole ratio, and then moles to mass using the molar mass of the substance within, which is effectively what this is. It's that calculation pretty much all mushed together. So that's going to be a very helpful, a little bit unique because of having the 2 numbers on top, but very helpful conversion factors. One more in this video, we're going to do a straightforward solution problem. So it's asking us kilograms of solution, and so we have 12.4%. Instead of doing moles on top, I'm going to do mass. Well, I don't need moles actually. I'm doing mass directly. 15.5 grams divided by grams of solution. And it's a percent, so it's times 100. And if I solved for my unknown there, I get 125 grams, which is going to equal 0.125 kilograms of the whole solution. Now, mass of solution, this is going to lead us into this next step in our concentration focus. Mass of the solution, if I've only got 2 parts, is going to be mass of my solvent plus mass of my solute. And I want to show you here that we've really got the mass of our solvent as well, which we would need for molality. So we have 125 grams here. We could find our mass of our solvent because we know this is 15.5 grams. Okay, so those are the types of things we're going to be working on next. And so hang on for the next video of concentration.